Hello, welcome to this screencast. I'm going to talk you through question 9 of component 2, which was a question about orbits. It started off with what I thought was a reasonably straightforward question, actually, but I think the first thing I'm going to say is look at my diagram at the top here. So let me see now if I can practice doing that. Here's my diagram. Now, I would never dream of doing an orbits question without labeling my diagram. Now, I've added information to this as I've gone through the question, so what you're seeing now isn't how it started. But I tend to label the big thing M1, the little thing M2. I tend to draw R1 and R2 on there and to draw D on, because if you don't, it's very easy to get confused about which you're taking as M1, M2. You can call it M subscript P or M subscript S for massive planet and massive star if you want. But the formula sheet's got M1 and M2, so I think it's easier to go for that. So I label them up straight away with M1, M2 and R1 and R2. It doesn't matter which way around you do that. And as I get information, you can see down here, I put R1 on there as soon as I calculated, but it was a little bit lower down. I think that way it's much easier to keep track of what's going on in the question. So the first one was a fairly simple one, but one that tripped a surprisingly large number of you up, actually. It's just time equals distance over speed. But in this case, it's 1,090 days and the speed is 45.5 meters per second. So it's just a matter of putting the numbers in and recognizing that if it's a circular orbit, that the circumference will be 2 pi r. So you can see the working there fairly straightforward. I hope you'll agree, even if you didn't get it right in the first instance. Next one. Specifying clearly any assumptions made. Almost always in these questions, particularly like this, where one thing is much bigger than the other, we just assume that in my case, M1 is much bigger than M2. The mass of the star is so big that we can pretty much ignore the mass of the planet. And therefore, in actual fact, D, the distance between them, is approximately equal to R2. There's an equation on the formula sheet. And when you put the numbers in, if you're careful, when you add them into your calculator, you get the answer that's shown down here. Let me show you something on the mark scheme here. So part 2, use of D equals the cube root of T squared GMS over 4 pi squared. They've used M subscript S for the mass of the star. You're not going to get any marks for just writing down the equation that's on the formula sheet. But in this case, if you rearranged it, if you did some work other than not simply write the equation down, I did try and give credit wherever I could. And so that was the answer that came out on the mark scheme. And my numbers are slightly different because I've used slightly different rounding things, but pretty much the same. And then having done that, we then had to determine the mass of the planet. There was a formula on the formula sheet. That's the method to the left down here. And if you work through it, like lots of you did, then you get an answer out. The correct answer is 4.4 times 10 to the 27 kilograms. That's what I got. I think the mark scheme is slightly different. 4.7 times 10 to the 27 kilograms. But actually, a much easier way of doing it, it's the same thing in essence, is a conservation of angular momentum method. M1R1 equals M2R2. And if you've written the distances in up here, R1 and R2. In order to get R2, all I did was subtract this answer, 6.82 times 10 to the 8, from D, which is what we worked out in part B. You get almost the same, 3.10 times 10 to the 11, rather than 3.11 times 10 to the 11. Very little difference because R1 is so much smaller than R2. But anyway, that's it's not a formula that's on the formula sheet, actually, but it's very often useful in these type of questions, as is, and now I'm going to try and write now with this pencil. The other one that goes alongside that one, which wasn't used in this equation, but one that is quite useful, is that M1V1 equals M2V2. Both of those equations, neither of them are on the formula sheet, but they're very often useful in orbit questions, so it's worth having them in mind if you're tackling these questions. So I think the method on the right was actually much easier to use. Right, let me go around deleting my stuff. There we go. So that was the answer to that question. And then we moved on to the second part, which is more about Hubble's law. So 2 graphs, and you're asked to comment on them and say something intelligent. I'm going to zoom out so I can see all of these now. bit too far, but I can see both graphs. If you're given a question like this, I think my advice would be numbers in the question, numbers in the answer. My first instinct was immediately to look at what was on the axes. So I looked at those values and I looked at these values, and then I compared them to these values and these values. Quite a lot of you said things like, there's a much bigger range. Well, you could do better than that. You could say, figure 1, the range of radial velocities is from 0 to 1,000 kilometers per second, and the distance is from 0 to just over, 2 megaparsecs. Whereas in figure 2, you get the idea. If there are numbers in the graph, do try use numbers in your answer. Quite a lot of you spotted that those things were the differences between them. Quite a lot of you struggle with the wording of what to say on this one to explain what's going on. Well, this one's much easier. The lines are all close to a straight line of best fit, whereas in the top graph, they're much more scattered. It's very optimistic, actually, to draw a line of best fit through those, a straight line of best fit through them. So you have to say something about that. And then the third point was that in the top graph, there are people said some negative values without actually acknowledging they were negative what? Well, they've got a negative radial velocity. In other words, they're heading towards us. They're not going away from us. So in other words, if you're trying to say the universe is expanding, then these points here are a bit embarrassing because it would appear to show that they're not expanding. They're actually moving towards us. They're blue shifted, not red shifted. Quite a lot of people said something vague like there are negative values. Well, negative values of what? This isn't just a maths graph. The units, the axes have units. So those are the way, that's my answer to the question. You can see my 3 answers there. And again, you can look at the mark scheme. So if you want to spend a bit longer reading what I'm saying, just pause me for the moment. But if we look at the mark scheme, you can see that it says pretty much the same thing as I've written, but they've used slightly different wording. So if you get a question, do think hard about how you're going to explain it. And then here we go. The calculation was fairly simple, I think. There was a mark for saying it was the gradient, so please do say that it's the gradient. Don't just calculate it, because if you get it wrong, you'll at least get a mark for knowing what you were doing. Some of you were terrible with this graph. I've drawn the intersection point here, so I can see that for 300 megaparsecs, it intersects this line at just under 20,000. The mark scheme was quite prescriptive. It said 64 plus or minus 2. I did give a little bit of the benefit of the doubt sometimes if people were just outside that range, but I probably shouldn't have done, actually. There's no excuse for being sloppy. Some people just said 30,000 divided by 500. Well, it's pretty clear that if you read across from 30,000, that intercepts well before 500. So please be careful when you're doing that. If you correctly did that, then you got the answer. I did 63.3 kilometers per second per megaparsec, which is approximately 63. And then all you had to do was to turn that into seconds, and then do 1 over h0 to get the age of the universe in seconds. But quite a lot of you lost a mark because you didn't read the question carefully enough. They wanted the answer in years, and that was the answer that you got there. So that is the end of me going through question 9. Thank you for listening.